In this video, we are going to talk about analysis of binary outcome variable. A most popular choice for regression for binary outcome variable is logistic regression. And there are actually several forms of logistic regression, so I especially call it binary logistic regression. So today we start with analyzing 2x2 contingency table. And many of you probably familiar with odds ratio and relative risk concept. And we will quickly review those concepts, and then we will talk about how to use logistic regression to analyze 2x2 table. And we will proceed to analyze data with 3 exposure groups. Okay, and we will cover another concept and what to do with multiplicity problems involving multiple groups, and we proceed with the pairwise test and test for linearity. In the last half of this video, I probably create a separate video for this. We will talk about binary logistic regression when you have a continuous independent variable, and especially talk about RC curve and calibration plots. Okay. And this table summarizes typical choice for regression with binary outcome variable. And most popular choice is a logistic regression. And logistic regression provides odds ratio. And not many people may be familiar with relative risk regression. We actually can do regression for relative risk. So in the course, chapter 20, I think it's 6 or 7, and we will talk about how to do relative risk regression, and especially we do use Poisson regression and with a little bit tweak using GEE. Okay. Although the typical choice for Poisson regression is when you want to compare rate. And if you remember, you learned in EPI course, and rate involves binary outcome variable plus time. Okay. And another analysis involving time is Cox regression. Okay. And so next week, and we will cover Poisson regression and Cox regression when we analyze binary data, but with consideration of follow-up time. Let's move on. In fact, there are more than one type of logistic regression we can perform. And mainly, there are 3 other types of logistic regression. One called the conditional logistic regression. This is often used when you have matched case control study. And other form of logistic regression is ordinal logistic regression, another terminology, proportional odds logistic regression. This is good when you have ordered categorical variable for the outcome variable. Okay, and for example, the disease severity, mild, moderate, severe, and 3 levels you have instead of a binary variable. And then lastly, there is a logistic regression good for multinomial outcome variable. A multinomial outcome variable is a categorical variable, and it does not have order in it. For example, you have a type of disease as outcome variable, like cancer, diabetes, and heart disease. You can't really put the order in it. And when you have this kind of outcome, multinomial logistic regression is a good choice for the analysis. So first example involves 2x2 contingency table. Let's look at the 2x2 table. And this data's outcome variable is esophageal cancer, and exposure variable is heavy alcohol consumption, defined by greater or less than 80 gram consumption of alcohol per week. So there are a total of 975 patients. I'm not really a big fan of 2x2 table, and let's use this format instead and see if you understand better. There are a total of 975 patients. Of those, there are 770 non-heavy alcohol drinkers and 205 heavy alcohol drinkers. Okay, And of those 770 non-heavy drinkers, 104 patients developed cancer, and the remaining 666 patients did not develop cancer. Of those 205 heavy drinkers, 96 developed cancer, and 109 did not develop cancer. Okay? And if you compute proportion would be like this. Okay? And proportion would be proportion of having cancer among a non-heavy alcohol drinker would be 104 divided by total number of 770. So that would be 13.5%. And similarly, within 205 heavy drinkers, and 46.8% is the proportion of patient with cancer. Okay? And to compute relative risk, you simply take ratio between these two. Okay, 46.8% divided by 13.5%. So relative risk is 3.47. So you may say risk of having cancer is increased by 3.47-fold with heavy alcohol drinking than non-heavy alcohol drinking. Okay. So today we use logistic regression, therefore we are not really using relative risk, instead we use odds ratio. So let's compute odds of having cancer. Right? And odds is really a number of events to number of non-events. So within 770 non-heavy drinkers, odds of having cancer is 104 to 666. And you take a ratio that is 0.156. And of those, 205 heavy drinkers and 96 has cancer. So odds of having cancer among heavy drinkers is 96 to 109. And you take a ratio, and that is 0.88. Okay? So to compute odds ratio, you simply take a ratio. So 0.88 divided by 0.156, and that gives you odds ratio. Okay? And quick review. And odds is usually larger than the proportion. So as you see, 15.6 is greater than 13.5, and 88 is greater than 46.8. And the odds ratio is always further away from the null than relative risk. So in this case, relative risk is 3.47 and odds ratio is 5.64. Okay? And when the event rate increase, okay, and odds ratio actually start exaggerating the value of relative risk. So you need to be very careful. Based on 5.64, you can't really say the risk of having cancer increased by 5.64-fold. If you want to say that, you have to be using relative risk. Okay? And so please be careful when you present odds ratio. As long as you said odds of getting cancer increased by 5.64, it's okay. And you just don't say risk is increased by 5.64-fold. So this is the result of chi-square test. And chi-square tests show association between heavy alcohol drinking and esophageal cancer. Esophageal cancer is highly significant. Okay? And the odds ratio is 5.64, that matched with our hand calculation, and 95% confidence interval is 4 to 7.95. And how do you use confidence interval? We need to check whether the null value is included in this range. What is the null value here? It's a ratio, so null value is 1. 1 is not included in this confidence interval, therefore, and you would think p-value would be less than 0.05, which is true in this case. Okay, so let's analyze this data using SPSS. So if you open data using a file called esophageal cancer.sav, And this is a data set. And you may wonder, this data format is not the format you typically see. And you might expect large data set include 900 something patient, 900 something lines, right? And although this data set have only 4 lines, and this is actually the summary data. So here you can see there are 666 patients and who is not heavy alcohol drinker and didn't have cancer. And there is 109 patient and alcohol drinker, heavy alcohol drinker, and didn't have cancer. So, so this data set directly input frequencies. And you can analyze this type of group data using SPSS. Okay? And when you have group data, you need to weight each line by number of patients so that SPSS realize this is not one patient, it's one line. Typically, it recognizes one patient, but in this case, we will tell SPSS this consists 666 patients. Okay, so how can we do that? And you go to data and weight cases. Okay, so we tell SPSS, and we have to weight each line by this frequency variable. Okay, so whenever you see group data, and you need to go through this step, and otherwise SPSS may misunderstand you have only 4 patients. Okay, so that's what this slide says. All right, so let's review how to do cross tabulation in chi-square test. So you go to Analyze, Descriptive, Cross Tab, okay, and you put cancer and alcohol, right? And you don't have to worry about which to put the row, which to put the column, as long as you know how to interpret 2x2 contingency table. Okay. And you click, if you want to have chi-square test done, and click on statistics and click on chi-square. If you want to compute odds ratio, and click on risk. Okay, and we are ready. And continue and OK. Right? And SPSS computed or created 2x2 table for you. So here you can see there are 770 non-alcohol drinkers, and of those 104 patients had cancer. Similarly for heavy alcohol drinkers. And it is helpful if you can actually compute percent for this. So let's put percent. We are going to compute percent within each column. So you go back to cross tabulation, contingency table, click on cells, and click percentage for column. Okay, and continue. Okay. Right. So now your contingency table have percent. So if you want to compute relative risk, you simply take ratio between 46.8 divided by 13.5. Okay, and you can compute relative risk. And this is a p-value based on Pearson chi-square. Okay, so when you have less than 20 patient total, you may want to use Fisher's exact test, but in this example, we have sufficiently large number of samples, so we do use Pearson chi-square p-value. Okay, and this is a result by clicking that risk button. So you have odds ratio here and confidence interval, 95% confidence interval for that odds ratio. And surprisingly, you don't see relative risk here. So SPSS does not compute relative risk. And that's too bad. So this lecture is actually regression. We talk about regression. So we no longer use Pearson chi-square test. Instead, we use logistic regression to do the same analysis. Right? So let's proceed. So now we use logistic regression to compute the same odds ratio. Okay? So you will see regression can be replaced with those univariate tests. So if you know how to do it with regression, and you don't have to conduct Pearson correlation coefficient, Pearson chi-square test anymore. And good thing about regression is we have big box for covariate. So if you want to make adjustment for other variable, you can do that. Pearson chi-square test can't do that. Right? So let's go to SPSS and go to regression binary. Okay? And outcome variable is cancer. Exposure variable is alcohol. Right? So here is a rule in the covariate box, and you need to make sure this variable is either binary variable or continuous variable. If you have categorical variable, okay, and you need to click this button and let SPSS know this is categorical variable. Right? And we will do this in next example. But here, alcohol is binary, so you don't have to worry about it. Okay? And then let's go ahead to make sure we need to click other button. So here, click on confidence interval. So this is a result of logistic regression. And beta coefficient for alcohol drinking is 1.73. This is not an odds ratio yet, and you need to exponentiate it to get the odds ratio. So 5.64 is odds ratio of cancer by heavy alcohol drinking, and this is 95% confidence interval. And minus 1.857 is an intercept. Okay. So we will talk about how to make sense out of an intercept. Although when you want to see association between exposure and outcome, all we care is this beta coefficient, not the intercept. Okay? So based on this analysis, what can we conclude? Odds of esophageal cancer is 5.64-fold increase among heavy alcohol drinkers compared to that of non-heavy alcohol drinkers. And the p-value is less than 0.001. And the confidence interval is 4.00 to 7.95. First key point is result of logistic regression. Beta coefficient, especially exponential beta coefficient, provide odds ratio. And using odds ratio, we can analyze effect of exposure and outcome. In fact, binary logistic regression can estimate not only odds ratio, and it can also estimate probability of events of interest. Okay? And using the following formula. What is the probability of events of interest? Which is we just compute it by hand. It's this one, okay? And probability of having event within each group, 13.5% and 46.8%. So we can actually get this absolute risk based on logistic regression. So this is a formula. And what you do is you plug alpha, which is this value minus 1.857, and you plug beta, which is 1.73, okay? And beta times x. X would be 1 for heavy alcohol drinking, 0 for non-heavy alcohol drinking group, okay? And do the same thing here. And then you compute this out, and that's how you compute probability of events, not the odds in this case. And let's do that. All right. So classroom exercise. Let's compute probability of having esophageal cancer for heavy drinker. Okay. So using this formula, let's compute probability of having esophageal cancer for a person who is a heavy drinker. And also let's compute probability of having esophageal cancer for a non-heavy drinker. Okay? So you use this formula. Okay? All right. So next exercise, I'm asking to compute odds of having cancer among heavy alcohol drinker and also among heavy alcohol non-drinker. And how do you do that? Right? And in fact, linear component of logistic regression, which is intercept plus slope times x, is log of probability over 1 minus probability of event, which is odds. The linear components of logistic regression is log of odds. Okay? And therefore, to get the odds, you just exponentiate this linear component. Okay? So exponential of alpha plus beta times x. X is 1 for drinker and 0 for non-drinker. And you know what is alpha and what is beta. Okay, so you know how to answer number 3 and number 4. Okay, so given this, quick question. What does the value of the beta coefficient for heavy drinking indicate? What does this beta 1.73 indicate? That's easy, which is log of odds ratio. Okay, and then here's a tricky question. So what does value of the constant intercept indicate? What does minus 1.857 indicate? So that's this question, and I let you think about a little. Okay, so you get the alpha when this part disappear, right? So how can we let this part disappear? To plug 0 here. Okay, what is a 0? Non-heavy alcohol drinking. So exponential of alpha is exponential of minus 1.857 is odds of having events among non-alcohol drinkers. Okay, so let's compute. Okay, which is 0.156. Let's make sure it matches with our hand computation. 0.156, yes, it matched. Right? So take-home message from this exercise is, many people think logistic regression provide only odds ratio, but instead, and we can compute probability of having events. Okay? Okay, and linear components of logistic regression is log of odds of having events in either of exposure group.